Welcome everybody to RISE Learning Machines seminars. I am Olof Mogren and I am a researcher at RISE, which is Sweden's public research institute. Learning Machines is our open weekly seminar on AI and machine learning. The meeting will be recorded. Let us know if you want to be removed from this recording. And also check out the collection of great talks on our YouTube channel, where this recording will end up after a short editing. Today, I have the pleasure to introduce Felix Köhler, who is a PhD student at TU Munich. He is a fourth-year PhD student, I should say, under the supervision of Professor Niels Thuret. Felix research interests spans numerical simulations of PDEs, reduced order models, neural emulators, optimization theory, automatic differentiation, and adjoint methods. Today, the topic of this seminar will be from numerical simulators of PDEs to neural emulators and back. And with this said, I will stop my screen sharing here and hand over the floor to you, Felix.
Yes, thank you a lot, Olof. I will start sharing the screen. Okay, let me see. Okay, wonderful. Should be visible, right? Great. Okay, then thanks again for the introduction, and I'm very happy to speak here in the seminar. Olof already introduced the topic. It's called from numerical simulators, PDEs to neural emulators and back. It is roughly based around two of my latest papers, but put into a bit of a more narrative arc and with some tangents. And I hope it will be interesting to you, and I'm happy to take your questions after the presentation. I want to start with a motivation of why the simulation of natural phenomena is important. And I brought a couple of examples, roughly ordered by the scale of the particular problem that is being tackled. On very small scales, we find the simulation of molecules or atoms, quantum simulations. And this is a useful tool for material and drug discovery. And I guess the importance of that is quite obvious, as new materials might help us build better products, and drug discoveries, of course, might us help combat diseases. And often overlooked application of the simulation of natural phenomena is in the field of visual effects or game physics. And I'm sure you're probably also excited for the third installment in the Avatar series, which will probably have a lot of special effects. And of course, those are to some extent also the simulation of natural phenomena, but with a different goal. Of course, they want to achieve plausibility, immersion, and entertainment. But of course, we are kind of drawn to these movies because they are so nice to watch. And a lot of games also make usage of the simulation of natural phenomena. I think by now very old example is this World of Goo example, which is like some essence of structural mechanics, which also is fed back into a gameplay loop. And so here there's also some importance for these simulation. You of course have them in engineering. Here I have the example of the external aerodynamics of cars. And if done correctly, these engineering simulations give us insights into the science and would allow us to build safer and in the best case also more efficient products. And on some very big scales, you will find this in weather, climate, or even astro simulations. And there they help us understand these really complicated systems, do weather prediction, precipitation prediction, and also understanding the impacts of climate change. And typically when we do simulation that follows a path like this, and we usually start by observing the nature. And here I just took a stock image of a lake in Sweden. I thought that would be fitting for the presentation. And we just choose, let's say for now, a little bit of an abstract representation of this. And I guess for the meme lords among you, you might recognize this image. It's from by now quite an old meme of how, in quotation marks, normal people see the world, and how scientists and engineers see the world in the descriptions of reality, often in terms of partial differential equations that describe all these natural processes that surround us. But the problem with these approaches, even though they are good descriptions of reality, is that they do not immediately describe or give us solutions of how the reality acts in specific cases. And so we have to resolve them. And oftentimes, or at least I would like to call this the simulation of these models. And that is often done computationally with numerical approximations. And this then produces oftentimes three-dimensional fields or with an additional time axis. Oftentimes, for many applications, the fields themselves are not that interesting, but some derived quantities, which then give us insight and are fed back into a feedback loop. But in certain applications like visual effects or computer graphics, also the entire field can be of interest. The problem here, and the problem that neural networks would like to tackle, is to improve this costly part of simulation. Because especially in these more complicated cases, think of very high fidelity effects in feature movies, or think of high resolution representations of car models. This is very costly to resolve. And the hopes is that neural networks can accelerate this. So the question that my talk is centered around is, can we approximate simulations with neural networks? But I want to tackle this a bit from a different angle. And for this, I want to clearly state a simplification that will be done throughout the talk, is that I will not look at the problems of, let's say, external aerodynamics or weather or climate systems, but rather look on more abstract PDEs on regular periodic grids in 1D, 2D, and 3D, for which you can see the spatial representations here. And I find this super interesting because for multiple reasons. So we do have building blocks or prototypical PDEs that we can solve on these regular grids, which already give us quite a lot of insights. And they are the building blocks for many of the more complicated phenomena, like the external aerodynamics or weather and climate. So it is reasonable to assume that the insights that we gain from these more abstract experiments might translate into the more complicated settings. And on the other hand, these particular choices also allow us to gain theoretical insights, which will become important in the second half of the talk. And even if I cannot convince you that this is interesting, I just brought some visual animations of how such phenomena could look. So for instance, an example we will look at a lot is an advection equation, which is just a simple transport process. And you here also see these periodic boundary conditions, something that exits on the right, re-enters on the left. Can also be plotted spatio-temporally, like with time on X and space on Y. Also be done in 2D and 3D. And especially if you look at the 3D example, that already looks quite challenging. And if we want a network to approximate this, this is actually not trivial. And we will also look at nonlinear equations. So a typical example would be here a Burgers equation, which does not just transport something, but also creates more high frequency information in the form of shocks. And we will also look at chaotic problems. So in 1D, an example would be or 2D also the Kuramoto-Shibashinsky equation, which could be related to how processes happen in combustion. And of course, as a prototypical example of chaos is also an interesting insight because a lot of the natural phenomena are inherently chaotic. Okay, how do we learn neural networks to solve these kind of problems? And for this, I want to operate on a state-discrete representation. So we use the grids on which these simulations are already defined. And then we want to learn so-called autoregressive emulators that map from one time frame to the next. And if you look at this, especially in 2D, I think that's quite clear when you have these regular grids, that it's nothing else than an image-to-image task. So we can actually take a lot of the architectures from computer visions that would be used, for instance, in image segmentation and apply them to this kind of problems. And then how do we train these? Typically, we generate data by fixing one specific PDE. So again, looking at this example of the advection equation, create trajectories with varied initial conditions and roll them out for a couple of time steps, and then create all these frames here. And out of these trajectories, we can sample windows of size of 2, split them into input and output. And then essentially, this is just a supervised learning problem. I would like to call this the one-step supervised learning problem. And it's a very classical deep learning pipeline to optimize our network here. And the first network I would like to plug in here is a convolutional network, because I guess that's also the most, the first choice one would choose in an image-to-image task in computer vision. And for this, I ran an optimization for the advection equation, and I would like to show you a learning animation. But before I show this, it is interesting to keep in mind that there is this discrepancy between what we learn on and what we want the networks to be good at. So we learn them to predict the next step into the future across multiple trajectories and across multiple time steps. But eventually during inference, we of course want them to produce long trajectories. So they will be rolled out during inference for multiple time steps. And it is interesting to observe that these networks can learn the long-term behavior just from being presented with this one-step loss. And these differences between the training and testing will be a core thinking point for the second half of the presentation. But let me play this animation for you. So essentially what you see here is this convolutional network over the optimization process. It's a bit oscillatory because it is sampled at longer intervals, but eventually towards the end of the training, the network stabilizes and is able to predict this prediction, this advection behavior. And especially if you run the animation again, we do see that it is more oscillatory, of course, the further in time it has to predict because of all the autoregressive accumulation of error that happens. But still, it is able to stabilize and reasonably predict for 200 time steps. And in the bottom, you see an error rollout here in terms of a normalized root mean squared error, which is then roughly at 0.4 after 200 time steps, which would indicate a decent performance of the network here. Okay, so this at least answers the question well. Okay, it's an advection problem, but at least networks are able to learn these PDE problems. But what I would like to present for the rest of the talks are some deeper insight in what these networks actually learn and how their performance varies if we change different PDEs or if we change different architectures. And for this, I want to present results from 3 different emulation scenarios of the advection equation. Because the same advection equation can be in like multiple different settings depending on how fast the information is transported. So on the left, we have something where the information travels very slowly. So the angle in this spatial temporal plot is very low. And we can increase that, go to faster speeds, bigger angles, and very fast speeds. And if you look at this here, there's a way to parameterize this. I don't want to go too much into detail, but at least the important thing is that this can be related to how many cells or how many pixels, you might say, the information travels. And in this particular case, the information travels 0.5 cells, here 2.5, and here 10.5 cells. And I think that's also directly visible in these choppy frames that the solution moves by quite a bit. And now it's interesting to see how convolutional networks can emulate these particular problems under these different parameterizations. And for this, I want to start with the first example of 0.5. And here we basically see a test rollout, so basically after training of 4 different convolutional architectures for this slow, low-speed advection problem. And the way these convolutional architectures differ is in their depth. So meaning how many convolutional layers are stacked on top of each other. If we only do 0, so in that terminology, this means we have a 0 hidden layer, which should be a linear convolution. This would mean we have a receptor field in our convolution of 1 in both directions. If we do 1, then it would be 2 because we stack multiple layers and so on. And I did this here for 2 and 10 as well. And then we see that under this particular setting, all these architectures work. How do I know that they work? That's because the error growth is linear. That usually indicates that they are stable. If it was exponential, that is usually a signal of instability. But we also clearly see that the architectures with smaller receptor fields, or these smaller convolution architectures, do not perform as well as the bigger ones. And it is interesting because the problem, this dictates a certain receptive field, and all these architectures do have this receptive field, but only the bigger architectures seem to work the best here. It becomes more interesting if we extend this and go to the other two parameterizations of the advection problem. At 2.5, for instance, convolutions of depth 0 and 1 are insufficient or do not have enough receptive field to see where information could come from. And then we immediately see that they are unstable in terms of exponential error growth. But on the other hand, with the problem with 2, it does have some regime of stability and then starts to explode, which I think is because it has not have this additional slack, so there's not this additional capacity to be really good at this. Whereas the 10 example works well, but then all of them fail, and also the 10 one, despite having sufficient, but I think with the same reasoning. And now it becomes very interesting if we add more classes of architectures to this. So here I add 4 more architectures, and essentially these can be classified into 3 different categories. So the blue and the green one are basically local convolutional architectures. So we have convolutional nets, which are just stacks of conv layers. ResNets just have additional skip connections, but conceptually very close. And then we have what I would call long-range convolutional architectures. So architectures that have an inductive bias to look very far. So for instance, units, which achieve this by having hierarchical representations, or some dilation networks, which do this by dilating the convolutional filters. And the third class of architecture is so-called pseudospectral architectures. The prominent example here is the Fourier null operator, and they operate by using spectral convolutions. And then what we see here is that under the low speeds, we see that the local architectures, the blue and the green curve, are the best. And the architectures which have very wide receptive fields, the red and the orange ones, do work, so they're stable, but they're not as accurate because they spend a lot of parameters on interactions which are not needed. But this, of course, becomes important when we then go to the very fast-moving dynamics, and then those are stable, whereas the short-range convolution architectures are not. An interesting example is the FNO, which is almost agnostic to the speed of the advection problem. And so that's an interesting insight, and I think I will make usage of that again in the second half. And to spoil this a bit, in this case, this is caused because the problem is very beneficial for the Fourier null operator to learn here, because we are on periodic boundary conditions, and also the reference data is generated with something that is based on spectral convolutions. And now I want to present the results of these emulations for more PDEs. And for this, I will compress the error rollout into aggregated metrics, such that I can show more data in one plot, essentially. And here, the example I would like to show is how these networks perform when emulating the Burgers equation in 1D, 2D, and 3D. The Burgers equation is similar to the advection equation in that it is also a transport process, but as we saw before, it also creates these shocks or sharp gradients, so it is not a linear problem. And we again see that the local architectures work best because the Burgers is parameterized similarly to the advection equation and being fairly slow here. The long-range architectures work slightly worse. And then the pseudospectral architecture, interestingly here, does not perform as good anymore. And that's because the spectrum or the representation of the states become quite rich if these shocks are being developed. And what we saw across all these experiments is that if the spectrum is too rich and we use a pseudospectral architecture, it can sometimes not capture it. I mean, it does, so it's still working, but it's not as good as a local one. If we go to 2D and 3D, we see 2 interesting trends. So the first trend is that apparently the additional skip connections, which is the difference between the conv and the ResNets, become more important if we go into higher dimensions. So we see that there's a widening gap between the convnet and the ResNet. And we also see that apparently the mechanism that the UNet uses to achieve long-range interactions is better suited for the 3D case than the dilation. And I guess that also kind of mirrors the more prominent usage of UNets in computer vision than dilated architectures. And we did a lot more experiments. I will just highlight this here that we did all these experiments. I don't want to dive too deep into all the details. Just a highlight on another class of PDEs that we tested, which are so-called reaction diffusion equations, which are problems with inherently very rich spectra. And in these cases, we again see the trends that, for instance, these pseudospectral architectures do not work as good because they cannot capture these rich spectra. And when we conducted all these experiments, I tried to compress this into an architecture decision tree. And essentially, if you read this, we tested 3 different PDE classes, or we classified this like this, which were like linear problems, problems which are like fluid-like. So they have characters of how you would model fluid phenomena, or these aforementioned reaction diffusion equations. In the case of linear and fluid-like, we further distinguished whether the spectrum is limited. So meaning if the solutions are rather smooth, either in the beginning, or they also don't develop and they also stay fairly smooth. And in these particular cases, the FNO is the superior choice. If that is not the case, we further distinguished if the dynamics are fast or slow. So this is some parameterization mechanism we used here. If you're curious, we can discuss it more in the Q&A, but the point is that if it is fast or slow, if it is slow, then the local convolutional architectures are the better choice, and especially the ResNet for the higher dimensions. And if it is fast, of course, information travels through the through large parts of the domain, then we need these long-range architectures. And in 1D, we found the dilated mechanisms to be better, and the UNet in 2D and 3D. And the interesting thing in presenting this is if you were to give such a decision tree to someone who works in numerical analysis in the simulation of PDEs, he would choose very similar numerical methods for these particular type of problems. Why am I saying this? So the architectures that we see here, so for instance, the Fourier null operator, as I already mentioned, is very close to pseudospectral integration schemes. And ConvNets and ResNets, by their convolutional or cross-correlational mechanism, can also be related to explicit integration schemes, especially based on finite differences. And one could, for instance, interpret UNets as some form of multi-grid solvers, which are a very good choice for problems with long dependencies, like we see in Poisson structures, for instance. And so if you were to replace the architectures here with similar numerical schemes, I guess most choices would be identical here. And so the conclusion we had from this is that the architecture that works best for a specific type of problem is usually the architecture with the closest similarity to the numerical method you would also choose to solve that type of problem. And this is just like a small summary of a paper I presented last year at NeurIPS. What I find so cool about this paper is that the insights we draw are based on this pip installable package. So it is in some sense a bit of a strange benchmark because you don't have to download any data set. It is procedurally generated, and this also allows you to experiment a lot into what is the effect of certain configurations of PDEs and certain architectures to draw these conclusions that I just met. And I'm pretty sure there are multiple axes which are still not investigated with this, and some of it which I, unfortunately, for the sake of time, I couldn't show here. But if you're curious on this, I encourage you to check this out. Okay, but let's move to the second part of the talk. So we already gained an insight into a wide range of architectures for solving arguably a bit more of the abstract, but at least for solving a wide range of PDE problems. And I guess I'm pretty sure one could take some of these insights and then map them to more complicated problems. But now I would like to dive even deeper. I would like to more deeply understand what happens in these neural emulators if they learn this particular PDEs. And for this, I want to recall the training problem of before, so the one-step supervised learning. And in the initial example I showed you, I put in here various convolutional architectures. So we had like with 0 depth, 1 depth, 2 depth, and so on. And now I want to make this even simpler. I will put in just a linear convolution without any bias. So I will put in an convolution with a kernel size of 2. Typically in deep learning frameworks, this means that they are biased to the right. No bias and just basically 2 learnable parameters. And then I will repeat the experiment that we've done before. So I will generate the data with the data generator that is in 8bench. And I train on this data. And then I can read what are these 2 parameters that we find here. And these are the precise values you get here. I think if you repeated this experiment, you would find them up to the 5th or 6th digit after the comma, because this is a convex optimization problem. So there's just one solution to this. And if we look at how these values perform, you can see this qualitatively in the top right with the model prediction against the ground truth and the difference. Yeah, it's doing fairly well. The error rollout here now shown in a logarithmic plot to show more of the spread is like a very typical curve that we see in these type of problems, that like it's growing quite quickly in the beginning because, yeah, it has to account for the fact it learned for 1 step and then generalizes to multi-steps, but then grows a bit slower towards the end. Okay, but why am I presenting this? The reason is because there is another mechanism to find these 2 parameters. And this other mechanism is based on first principles. So if you think back to the motivation I presented earlier with this path of simulation, this is the approach you would choose classically. So you would sit down, take a sheet of paper, assume a certain method. Here in this case, it's a finite difference scheme, and then derive what would be the method look like. And in this case, it would be, again, a convolution with 2 parameters, but the parameters are different. So under the specific PDE advection configuration that I looked at, they would be 0.25 and 0.75. So they would not be those values that we found here. And if you look at the qualitative rollout, I mean, first glimpse, it's almost as good. If I were to jump back, unfortunately, sorry, the figures are not really aligned, so it's a bit of a headache to look at this. But you would see that the FOU simulation, so actually that's the name of this method, it's called the first order upwind method, is a bit more blurry than what our other values are like. And that is also confirmed, that can also be confirmed if we put the error rollouts on top of each other. But since I guess it's a bit confusing right now what is going on, I would first like to present the schematic of what the experiment is that I'm presenting here. So again, we are trying to emulate the advection equation. And in order to do this, we used an spectral simulator. So that's basically the part that is in 8bench. And then for the advection equation on periodic boundary conditions, this particular tool is exact. And exact means that it does not make any form of error except for some small rounding errors. And then we use it to produce data trajectories. So these data trajectories are perfect. And then we have a functional form, our ansatz. So in the first half of the talk, that was like the convnet, the FNO, but now it's just this linear convolution. And for this, we can train both an emulator with a data-driven learning problem, as well as derive the simulator based on first principles. And if we compare the two, we find that the emulator performs better than this simulator. And that's interesting, right? Why should the data-driven learning problem find something better than what we can simulate, what we simulate here? And the answer is because these simulators, like the first order upwind scheme, are usually derived to work in all conditions. So they are derived to work in a wider range of potential initial conditions. Whereas here we had arguably, if we go back, we had arguably quite smooth states. So we had kind of a constrained operating regime. And in this constrained operating regime, we can learn something better just based on the data-driven learning problem. Unfortunately, there's of course a catch. The plot I present to you here only runs until 200 time steps. If we continue this and go all the way to 2000, we see that the first order upwind method is stable in that sense because it never goes above the 10 to the 0 threshold, which would be like indicating that the prediction is way off. But we clearly see that the emulator turns unstable after roughly 500 time steps. This is both good and bad. It's of course bad for the emulator that it's not stable indefinitely, but 500 time step is quite a bit. And of course, if your operating regime is 200 time steps, then we could be better than the numerically derived scheme, even when we use the same functional form. All right, let me put this into a bit more context. So what happened here? So typically when you, or at least how I would like to view it, if you want to solve a partial differential equation, let's assume that there were 3 different ways to solve it. So we again have in green the highly accurate exact solver. So for the particular problems that I looked at, they can even be solved analytically or almost analytically. And in all fairness, also very quickly, which is also the big advantage of Apebench, as I mentioned earlier, that it's procedurally generates our data, but that's just on a side note. But let's assume, and then there is another class of solvers, which you might call like a good solver, which would be a good choice for this, and another one which would be an okayish solver. And I would like to view this as not being 3 approaches which are where one is very good and one is very bad. It's more like typically a trade-off. So in practice, it is not that, it is of course that one would want to use the green one all the time, or the blue one at least, but for a lot of parts, only the orange one is the one that is feasible. And of course, what it concretely means to be the orange or the blue solver depends on the context. So it's a bit more loose here. Okay, but let's now assign 4 different tasks to these 3 solvers. So being the training data generator, to be the inspiration of the architecture, to be the test data generator, and to eventually be the baseline. And the case if the first 3 are the green example is exactly what we saw earlier when we used the Fourier null operator to emulate the advection equation. That the data was generated with a pseudospectral method. We used an architecture which is inspired by a pseudospectral method, and we produced the test data with a pseudospectral method. And as such, we saw, well, that works quite well. The setup I showed you before, so this one where the emulator beat the simulator, was the following. So we produced data with the green one, used the blue one as an architectural inspiration. So we used the first order augment method, which is a decent choice for advection problems, and use it as an architectural inspiration. We produced the test data using the green one, and also had the blue one as a baseline, and then found out that based on the fact that we are constrained to, well, we only need to work well in a couple of time steps, and the solutions are fairly smooth, we can find better parameterizations than our baseline. The setup I would like to consider now is the following. So let's assume we now use this orange category, the okayish solver, as our train data generator, but we will still use a good architectural inspiration. So we will again follow this, this decision chart as like, okay, this is this type of problem, so we better use such kind of a null architecture. And then we will, so in the examples I will show, I will use the green one as the test data generator. In practice, of course, one would try to be as close to the green one as possible. But here this is, to illustrate this, we will use the green one. And then we will baseline again on the solver, which also produced the training data. Okay. Before I show you some results on this, I want to re-emphasize the differences between training and testing, as I mentioned earlier. And I tried to keep the math as small as possible in the presentation, but I would still like to put in this. And this is to formalize what is the training and the testing objective of these autoregressive emulators. And the training objective, which I showed in schematics earlier, is this one-step supervised learning, which works like this. So we have a distribution of initial conditions from which we sample initial conditions. Then we use a numerical solver, here denoted as this color graphic P, and then this T shall be, say, okay, produce trajectory from this initial condition. And then from this, we sample consecutive frames, these two windows that I showed you earlier. And then in expectation over this distribution, we have a metric, this is this theta here, evaluated on the prediction of the network on the input versus what it actually should be. So this is what all the approaches are being trained for. But what are they tested on? And the test objective can differ. So for instance, we can have a different distribution of initial conditions. We can use a different metric. For the sake of simplicity, we will here use only metrics which are related to mean squared errors. And we can use a different solver to compare against, which is very crucial for the insights in a second. This is the, to go back, this is now the green one, basically. So in that sense, the solver we use for data generation here is the orange one, and this is the green one. And then also importantly is that we don't just predict one step into the future, but we predict autoregressively many. So this is meant by this raising to the t here. And then essentially we have errors at certain points in time. Okay. I also have this a bit more in a qualitative setting. So, sorry, in a schematic here. So what happens? We fix a certain PDE that we would like to emulate. And for this particular PDE, we have both the coarse solver here in orange, and we have the fine solver in green. We use the coarse solver to produce the trajectories given a certain distribution of initial conditions, and then choose a particular architecture inspired by a good numerical solver and learn on this with a one-step objective. And then importantly, we do not measure the error against the coarse solver, but we measure the error against the fine solver, the green one, but also produce a baseline score for the coarse solver. And then what I would like to define is the ratio between the whatever we measure with the emulator against the good solver and the coarse solver against the good solver. And then when this ratio drops under 1, we measured that the trained emulator is better than whatever it was trained on, or this data generator. And there are two types I would like to investigate and show you. The first one is what I would like to call state space superiority. So we call this superiority. It's of course a catchy name, but it's just meaning that it's better than the data generator. State space means if that occurs, if it is applied either to different initial condition distributions, or it's just because over the time, the distribution of the state space changes into something that has not been seen during training. Or it's because of autoregressive superiority in that it was trained on the one step, but then performs better during multi-step rollout. And what we found is if we take this specific setting of before, so we have in our blue one, we have a good architecture. We have in orange, we have like a somewhat suboptimal solver. I will explain this in a second what it is. And then in green, we have our high fidelity reference. This actually gives us a setting. And here these periodic boundary conditions that I mentioned earlier become very important again to mathematically prove that these superiority can exist, or specifically that state space superiority can exist. So under some assumptions, we see that if we train the emulator on specific data. So in this case, this is data with a relative mode of 0.01. What does that mean? That means, for instance, if we had 100 points, that the data only contains the first sign mode, because it's the ratio between the active mode and the number, the resolution. And if we then test on a higher mode, we see that the superiority curve dips under 1. And so essentially, the emulator that was trained at this particular information now performs better than the reference at more high frequent information. So for instance, evaluating it at the second sign mode. Okay, let's summarize this. So what did we learn? So essentially the first thing I presented to you in this more theoretically second part of the presentation is we took the spectral solver, which was perfect data. Then we took the functional form of the explicit method. This was the convolution with the two parameters. And then we found this was better than the first order upwind method. And then it's okay. I mean, it's a surprising result. Okay, it does not hold forever. It was still a surprising result, but of course it was based on perfect data. So we had a good functional form, but we had better data. Then another thing I did not show you is if you take Pluish data and train the Pluish functional form of it, this is just a convex optimization problem with a zero loss. You just recover whatever training generator was out there. But now the example that we looked at is we used an IO4U data, explain it in a second, like some mediocre data, use a good functional form, then we become better than this method. So we actually become superior. What is this bad method? So in the method that we associated the blue category to was the explicit method. And here the orange category is an implicit method. And for these advection type problems, especially under slow speeds, the implicit methods are usually not the best choice. So they have some inherent structural errors. And of course, these are present in the data that we train on. But what we see here is that under certain conditions, the inductive bias of the blue method can outlearn this. Okay, so far this is mostly about linear settings. So we have both linear PDEs, we have linear ansatzes, so in that case, these two convolutions. And so these insights are theoretically backed. But let's now move to something more empirically. And let's say let's go nonlinear. And hope this works. Ah, yeah, wonderful. And here basically we have the following setting. Let me run this simulation and then stop it towards the end. So essentially what we have is we take again the advection equation, initialize it with the first mode, so in that case, the first sine mode, and then produce a trajectory again with the implicit method. And we see, sorry, it's here, the implicit method, and we see it is overly smooth, or it overly smoothens out because it's numerically diffusive. And then on this, we train a neural network. It learns this particular behavior. So in comparison to the analytic solution, it's of course still diffusing, but it is less diffusive than our reference. So also qualitatively, we see here that it is superior. But how is this different from before? Because now the initial conditions are not from a different distribution. They are also the first sine mode that we trained on. What we see here is autoregressive superiority. So basically the nonlinear network, and that's something that only works if you have the nonlinearity. So you also cannot easily show this theoretically. I think probably there's no way to show it at all. But point is that the nonlinearity here gives rise to something which shows over the multiple time steps. And we can also see this on a metric. So if we look at the example of before, we see here the superiority rollout over time, and the ConvNet here in blue, this is the example I showed you in the previous slide, is superior from the second time step on. And that's very interesting because, of course, these autoregressive superiority can only exist from the second point in time on, because the distribution of what the initial conditions are drawn from are identical. We see here, interestingly, that the dilation mechanism is very strong at achieving superiority here. If you're curious, it's something we could discuss in the Q&A section later. But another interesting finding I would like to present to you here is I also tried this with a vanilla transformer. What does vanilla transformer mean? This means it's something which uses dense self-attention across these 1D grid points and considers them as tokens. And this does show superiority, but it's way weaker than all the other examples. And I attribute this because a transformer architecture does not have as strong inductive biases as the other methods. So in other words, there's no really good numerical method analogy to these dense transformers. If you were, for instance, try this with swin transformers, like these shifted windows transformers, I didn't do it, but I would think that they would show more superiority because of their convolutional-like inductive bias. And there's one more example I would like to show here is that if we also try this under a different setting, we see that the vanilla transformer does not show any superiority at all. So it's above what the other plots are shown here. In the sake of time, I will skip over some other interesting results. We can still go through this in case you want to discuss it after the presentation. But I would like to elaborate on what does that mean in practice. So the takeaway from this is, of course, there's a chance that we can learn superior representations. It is, of course, highly likely in a more complicated setting that this superiority will not clearly be visible because there might be other aspects in the network which actually make it inferior, and as such, maybe those then are more stronger in total. But it's likely to assume that at least some circuits within the network appear to be superior. But the more important takeaway from this is that it is actually very important against what we baseline. So a lot of the data that we use to train our emulators on does have structured numerical errors inside of them. And that's not a fault per se. It's because there's like a compromise when using numerical simulators. Oftentimes because that's the only way to make it possible, like for instance, running them at lower resolutions than what we should run them on. But oftentimes it's also done deliberately in order to save cost. So a typical strategy would be to truncate iterative solves or to use lower order methods specifically. And then, of course, this creates an interesting situation. If we draw our testing data from the same pool, we will never be able to see if the network might have learned something better. And this experimental and theoretical evidence suggests that they could at least do to some extent. All right. There's 2 more slides I have. So I first would like to reason what's next in this field. So some more trends which are, I think, interestingly, a bit orthogonal to what I presented here. So the first thing is people are now working on emulating larger 3D problems. So the problems I just showed you in the beginning, so these external aerodynamics, weather, climate, all the stuff which is quite a big engineering problem, especially when you work on unstructured grids. And another trend is to train foundation models for a wider range of dynamics. And the interesting insight there is, if you want to train a network that is good in emulating multiple PDEs at the same time or has a foundational understanding of what it means to emulate PDEs, you of course cannot, maybe if you constrain yourself to a certain class of PDEs, but in general, you would then want actually something which has lower inductive bias because you want it to be good at all the things. And there the interesting insight is that it seems that transformer architectures or something that is based on self-attention, which has a good computational inductive bias, but has very low, let's say, physically inductive bias, seem to be the best that work at scaling here. And as a shameless plug here, just want to advertise a work from our research group, which does exactly that. So using a transformer architecture to train foundationally on multiple PDEs. There are, of course, more works than this out there. The reason I'm highlighting this is because it used the pseudospectral method that I showed before to just generate like a lot of training data, something which I couldn't have imagined with ApeBench, but it's very cool to see that it can be used for this and then train in this new field of neural emulators. Okay, let me summarize my talk and what are the main takeaways. So first, which something we already clarified after 10 minutes, it's also, I think it's hard to doubt, but neural networks can be trained to approximate time-dependent PDE problems autoregressively. And if you specify a certain time horizon, they can actually achieve decent accuracy. Of course, it's a data-driven learning problem. It's very experimental. They will always be a little bit imperfect, but they have quite decent accuracy. Problem is, of course, we have little guarantees on them, especially no guarantees with respect to stability. Empirically, we see they are stable for hundreds of thousand time steps, but if we go into the 10,000s range, it sometimes gets quite tough. But what we also find is that if we have non-trivial simulations, so not the stuff that I showed you, but the stuff which is like automotive and clever and climate, they can speed up the solution process. So I never talked about timing in this presentation, partly because the solver that I used is so fast that it wouldn't matter to, there's no motivation that's based on reducing the cost. And especially if you think about it more holistically, in that not only being a tool which is better mathematically, but which is something that accelerates the entire engineering workflow or simulation workflow. And the second part is inductive biases are important for model performance. So the results from 8bench suggest that it's best to choose the architecture that matches or is inspired by the numerical scheme you would also choose for the specific type of PDE. And sometimes it is possible to have that the inductive bias outlearns structural numerical errors from some imperfect simulation data. And that concludes my presentation. As said, it's based on 2 papers of mine. One I will also present in San Diego at NeurIPS 2025. So if you are around, it would be nice to chat and talk, or you can come by the poster. It would be very cool to talk about it. And then there's also this 8bench paper. And as I mentioned, if you're curious, it is just one pip install away to play around with it. And I guess it's a very cool thing to do. Okay, thank you so much for listening to me, and I would be happy to take your questions.
Thank you so much, Felix. Fascinating stuff. Thanks. And you get the applause spread out over internet here.
Thank you.
So please, everybody, come up with your questions to Felix. And while you do, I'll chip in a question or two. When you were talking about the foundation models in the end, and you were talking about sort of that they need to be so general and they need to have less of this inductive bias, and a lot of the things you've been talking about is the inductive bias and how that can help you get this superiority. How would you go about if you start out with something like foundation model? How do you turn that into having the right bias when you fine tune it?
Oh, that's a very good question. I mean, what we see in fairness is that most of the foundation models that are now out there here are either inspired by Swin, so this shifted windows, or have something else which at least has a little bit of convolution in there. And I think this is a very strong inductive bias that they still choose to use. I mean, in the classical pipeline for foundation models, where you would, for instance, use some LoRa fine-tuning, your fine-tuning does not add any inductive bias. But maybe with respect to this, I could imagine that if your fine-tuning, for instance, consists of adding some new components to the foundation model, then it would be reasonable to choose those components that match for the particular problem you want to solve.
I mean, do you think there will be other things that in the architecture of neural networks that you can start think about, which will provide other step in this direction, provide another sort of level of the bias, which is something that you need in these problems.
So you mean if there's like I would say if there's like a new type of architecture that might be better suited for these type of foundation models, I think it's a bit hard to say. I mean, the community wisdom now goes towards the transformers. I think the problem is just that in these larger 3D scenarios, we rarely have the computational efforts to really exhaustively say if this is the right architecture to do this. So it's mostly just a bit of the wisdom of the crowd, what people are doing. And I think in those regards, it's also important that the architecture is not just has not just good physical inductive byte, but also computationally. And I just think that these self-attention mechanisms with all the potential tricks one could employ there are just very good at scaling to larger resolutions and to something for which other stuff might be harder at. But of course, there are also tricks you could do with other architectures. So it's a bit hard to say. At the moment, I would also say that transformers are the best direction, but I also don't have a good alternative direction for this. But of course, transformer is like the envelope category, and of course you see many sub genres of the transformer foundation model.
Time will tell.
Yes, absolutely. That's the interesting thing about science. Yeah.
Yeah. Linus has raised a hand.
Yeah. Hi there. Thank you for this. I was wondering, I guess, on the other side of things here, when you have these architectures inspired by the solvers in terms of the inductive bias, is there an automated way to sort of map from one to the other to get the right inductive bias for a certain type of PDE? And is there an automated way of doing that, or is it kind of you manually look at it and you decide, okay, this looks more like the CNN would work or something?
Yeah, that's a very good question. So in the architecture decision chart, let me quickly jump to the corresponding slide. So there I use this, I said low, gamma, and delta, and that's something I did not explain, but in ApeBench we used a parameterization scheme, which allowed us to describe a lot of different PDEs with just like 5, 6, or 7 parameters, which you then have to vary, and those gives you different dynamics. Maybe I even have an animation for this. I don't know. Probably not, but point is they allow you this. And what I can imagine is that it's nothing we did do, but I think it's something one could do, is that you could do find like classification boundaries in this 6 or 7 dimensional space for what particular architecture is the best choice in that. So I think that would allow you to do it automatically. But I think the interesting analogy also here to numerical simulations is that I feel that many numerical simulation experts would also choose this mostly based on intuition. So they do have an intuition about, okay, this particular phenomenon behaves like this, and so maybe this is better. And to some extent, it's also disputed what particular method is the best for one thing. But these are the 2 ways I would answer the question. So the first is for the ApeBench, one could do it in an automated way, maybe even with some machine learning on top to find the classification boundary. And in practice, I guess it's still a bit, it's kind of like choosing a neural architecture in a computer vision task as well. There's also a bit of debate of what is the best.
Yeah, okay. Thank you.
Thanks a lot for the question.
We have a raised hand from Kara.
Yeah. Hey. Well, thank you for the talk. It was really interesting, and I think it's awesome work.
Thank you.
You actually skipped over like the shock equation, so that I was interested in that, mostly because so I'm wondering if you have also been testing on like PDEs that have like critical behaviors at some point. I'm thinking mostly about, so you named shocks, and that brought to mind like magnetodynamic aerodynamic equations. And as far as I know, they can have like very narrow minima, which like if you coarse sample like the parameter space, then it might be very difficult to find. So have you thought about it? Have you experimented with that?
Oh, yeah, so it's a very good question. So so the particular problems that I looked at were of course limited by whatever I could generate reasonable reference data for. So even if I go back to these animations. Even here, I mean, I guess you would see that this is a very smooth version of the Burgers equation, so it's not super sharp. And that's, of course, caused by, oh, sorry, this was not what I wanted to do, but okay. Anyway, but there's that's based on me using this pseudo-spectral method as a data generator, and so I'm limited to smoother problems. I'm not too familiar with the magnetohydrodynamics, but I guess there you would then also have more sharper interactions, and usually also what you would see numerically is that the problems with the very sharp interactions are also really hard to simulate, and so
So, but I'm even like forgetting about the actual like magnetodynamic simulations itself, where you also have shocks and everything. Like like if you look at the non-time independent version of those equations, you still see that they have like they're not really singularities, but like they are like very, very narrow minima. So it is very complicated, like to get to a solution anywhere, and it would be great if you could actually help with an alternative method, because like the semi-numerical or like simulation methods are really, really, they have a very hard time, and they require a lot of expertise to even get close to an exact solution. So like if you could emulate that would be really, really good.
Yeah, I think it's interesting. Maybe one thought to add is what all these what all the neural networks are bad at, and this is not just in emulating PDEs, but also you see this in other applications, is to really fit the high frequency information. And I guess if you have these, if I hope I understand you correctly, if you have these narrow minima, this would be like very high frequent information that in order to see this see this visually and also represent it. And so the networks tend to be very bad at fitting this. I guess there are multiple approaches to make it better, but it is still an open problem, and I'm unsure if it is even solvable with deep learning. I mean, I to be fair, I haven't read it, but recently there was this this big announcement of the usage of pins for finding some special behaviors of the Navier-Stokes equation. I was actually quite surprised that that this would work with pins. So maybe there's some work in this regard, but I'm not too familiar with it. So how I would put it is, I think these emulators are very good in these domains in which most of the derived insight comes from smooth to medium smooth problems. And if the problem is very high frequent or has like really high fidelity information, it is first of all very hard to generate the corresponding training data, and on top it's very hard to fit it, and then of course it's also quite hard to rely on it, or it's like it requires a lot of trust. So yeah, that's how I would answer it.
Thank you very much. Like I could maybe have some data on that you on exact solutions that you might maybe want to use it if you are interested in that. So yeah, maybe let's keep in touch.
Yeah, that would be nice. I would be curious to check it out and see what these networks do.
Yeah. Okay.
Thank you.
Thank you.
Cool. I think we should start to wrap up this seminar. Thank you so much, Felix, for this amazing talk and this interesting discussion. We'll meet again next week, actually. So November 30th. We'll have Nora Gourmelon from Friedrich Alexander Universität Erlangen-Nürnberg. She's talking about self-supervised pre-training for glacier front extraction synthetic departure rate. Welcome back, Thursday.
Thank you.